Good day, viewers. My name is Sherry Poshoreko. Welcome to our program 1 of our computer study series for the grade 10 and 11. Our topic for today will be on logic gates and circuits. Now, before we get into details, let's just quickly look at the objectives. Right. Number 1, recognize different symbols of logic gate. Number 2, interprets logic circuits using truth table. And number 3, finally, produce a truth table for different logic circuits. Alright, viewers, when we talk about logic gates, what are we talking about? Logic gates are the basic building blocks of any digital system. Right. It is a circuit having one or more than one input and has only one output. Now, before we discuss how it works, let's first look at the different gate symbols and their names. Viewers, there are common symbols used to present logic gates. The first one is NOT gate. Secondly, we have AND gate. The third one, we have the OR gate. Fourthly, we have NAND gate. Then we have NOR and XOR gate. Note that when it comes to the NOT gate, it has only one input, but all the others have two inputs, as you can see. Right, viewers, let's move on. We use truth table to show logic gates function. Now, truth tables are used to trace the output from a logic gate or logic circuit. Remember that NOT gate or the NOT gate is the only logic gate with one input. The other 5 gates have 2 inputs. When constructing truth tables, all possible combination of 1s and 0s which can be input are considered. Right. The possible inputs are determined by the number of inputs. For example, 2 to the power n is the possible input, and note that n is the number of the inputs. Right. It means one input is 2 to the power 1, which is 2 possible inputs. Right. Now, for the NOT or the NOT gate, one input, there are only 2 to the power 1, which equal 2 in brackets possible binary combinations. For the other gates, 2 inputs, there are 2 to the power 2, which equal 4 possible binary combinations. Now, for logic circuits, the number of the inputs can be more than 2. For example, 3 inputs give a possible 2 to the power 3, which equal 8 binary combinations. And for 4 inputs, the number of possible binary combinations is 2 to the power 4, which equals 16. It is clear that the number of possible binary combination is a multiple of the number 2 in every case. Now, viewers, let's look at examples of the truth table for different gates. As you can see here, viewers, the NOT or the NOT gate acts as an event. It outputs exactly the opposite of the input. Okay, the NOT gate gives the opposite or inverse of the current output. Therefore, positive, all right, 1 or on becomes negative, which is 0 or off. while negative, 0 or off would become positive, which is on or 1. Right. Now, viewers, the A and D gate, both input must be positive, 1. Then the output is also positive, 1. X is equal to A and B. This follows that if A is equal to 1 and B is equal to 1, then X is equal to 1. Otherwise, X is 0 if A or B or both is 0. Right, viewers, let's move on to the next gate. That is the OR gate. Now, the OR gate, at least one input has to be positive, which is 1, to give a positive output, which is 1 or on. Right. Now, both inputs could also be positive. All right. Say, for example, X is equal to A or B. If A or B or both is positive, which is 1, then X is positive, which is 1 too. Good. Viewers, let's move on. We now will look at the N, A, and D gate, or not A and D. Now, it's very important to know that the N, A, and D gate is the same as A and D, but the inverse, which is not the outcome. So, perform A and D first, and then apply not to the output. The output, let's say X is 1. If input A and input B are not both 1, meaning that 0 and 0 equal 0, that will be not 0 equal 1. The next one, 0 and 1 equals 0, that will be not 0 equal 1. And then you have 1 and 0 equal 0, that will be not 0 equal 1. Finally, 1 and 1 equal 1, that will be not 1 equal 0. Viewers, the next one is the NOR gate. NOTOR is the same as OR, but then inverse, which is not the outcome. So perform OR first, then apply the NOT to the output. The output X is 1 if either input A, no input B is 1, meaning that 0 or 0 equals 0. That will be not 0 equal 1. We can also move on to the next one, which is 0 or 1 equals 1. That will be not a 1, which equal to 0. The next one, 1 or 0 equals 1. That will be not 1 equal to 0. And finally, 1 or 1 equals 1. That will be not 1 equals 0. Now, viewers, let's look at the last gate in our lesson, XOR gate, which is the OR, NOT, or both. This is when exactly one input is true and not both. The output X is 1 if, let's say, input A is 1 and input B is 0, or input A is 0 and input B is 1, meaning that 0 and 0 equals 0, since neither one is 1, right? And the next one, 0 and 1 equals 1 since one of the inputs is 1. The next one, 1 and 0 equals 1 since one of the inputs is 1. Finally, 1 and 1 equals 0, both is 1, therefore a 0 output. Right, viewers, we've been looking at the truth table with their respective gates. Logic gates. Now, logic gates are combined together to carry out a particular function, such as controlling a robot. They form a logic circuit. The output from the logic circuit is checked using a truth table. Right. Now, several logic gates combine together to form a logic circuit. And these circuits are designed to carry out a specific function. So, the following are the examples of the combination of logic circuits. Viewers, before we conclude our lesson, it's very important for us to look at what we have done. So far, we have looked at the symbols and described the use of AND, which is the AND, OR, NOT, NAND, NOR, and finally XOR gates. And we interpret symbol logic circuit using truth table. Viewers, before we conclude our lesson for today, please do the following questions. Number 1, identify the logic gate in the particular picture below. And finally, draw the truth table of the logic gate identified in A. Alright, viewers, we have come to the end of our lesson 1. I hope this lesson was informative. Thank you very much for viewing. Until next time, bye-bye.